Hello everybody and welcome to chapter 23. We're going to discuss transformers. Transformers transfer electrical power from one circuit to another. It doesn't change the circuit frequency during this operation. It uses mutual flux to transfer power. It doesn't use a cable, even though there are windings of cables. It can step up or step down the level of voltage and current. Read sections 1 through 4 in chapter 23. Michael Faraday discovered in the 1860s that electrical energy between two or more circuits can be transferred through electromagnetic induction. The transformer is an important component in our electrical power grid today, and it's used for a number of other purposes as well. Traditionally, one side of the transformer is called the primary, and the other side is called the secondary side. And there is a hunk of metal, and it's ferromagnetic material, and it's chosen to enhance the magnetic field. And this core serves to increase the coefficient of coupling between the coils of wire. There are a number of turns on the windings on each side of the transformer, and there is a relationship between a number of turns of coil and the voltages on both sides. Mutual inductance occurs when the change in current in one inductor induces a voltage in another nearby inductor. Our simple transformer has two coils, and the changing flux from one coil links to the other. If one coil has a supply of voltage, the other coil will have an induced voltage across it. The magnetic flux, the SI unit for that is called a Weber, named after Mr. Weber. There is a relationship between voltage and the number of turns. So we use the primary side voltage over the secondary side voltage equals the number of turns on the primary side over the number of turns on the secondary side. Let's do an example. Given a frequency 60 Hertz, primary side voltage 200 volts AC, secondary side 2400, that's a step up. And we have a number of turns on the primary side 50. Find the mutual and magnetic flux in Webers. Here's our formula that's given in the textbook. We'll rearrange that formula to find that flux. And we divide the primary side voltage 200 divided by 4.44, which is a constant, times the frequency of 60 Hertz, times the number of turns on the primary side, 50 turns. And we get 15 milliwebers. We want to determine the secondary number of turns. We'll use this relationship, plug in our values, and we'll find the secondary number of turns is equal to 600. Transformers are very efficient, and we'll say that an ideal transformer has no power loss. Electromagnetic coupling links one side to the other as long as the other coil is close by. Here are some important mathematical relationships between the entities, and as we talked about, the number of turns in the primary over the number of turns in secondary is approximately equal to the number of turns in the voltage primary over the secondary voltage. The turns ratio is known as the number of primary turns over the secondary turns. So let's do an example. Given 100 turns on the primary, 25 on the secondary, the voltage on the primary side is 120, determine the voltage on the secondary side. We'll use this relationship. There's one unknown. We'll solve for the equation doing cross multiplication, given 30 volts. So here we have a step-down transformer. The number of turns of the transformer and the voltage are directly proportional. Here's another example. We're given 100 turns on the primary, 25 turns on the secondary, primary voltage 100, and we'll solve, find the voltage on the secondary side using this relationship, 480 volts. Now it's a step-up transformer. A step-up transformer can take a low voltage and boost it to a higher voltage level. A step-down transformer can take a high voltage and reduce it. Looking at the transformer ratio, it's the number of turns on the primary over the number of turns on the secondary. If that relationship is less than 1, transformer is a step up. If this relationship is greater than 1, it's a step down transformer. Determine the secondary current, IS. So in this relationship, currents are inversely proportional to the number of turns. So we'll plug in our values here and we'll find that the secondary side is 40 amps. Power on both sides of a transformer, of an ideal transformer, are equal. When we have a step up or step down transformer, what's changing? The voltage is changing, and we'll notice that when the voltage goes up, the current goes down and vice versa. And we'll see that in our calculations. The reflected impedance is often referred to as ZP in this equation here. If the load is capacitive or inductive, so is the reflective impedance. Keep that in mind. Also, power in is equal to power out under ideal conditions. Let's go over this example here. So we've given a number of turns, primaries 100, secondaries 10, and the secondary resistance or impedance is 8 ohms. And we want to find the impedance on the primary side. We can use this relationship here, and we'll square these number of turns here, relationship, times the secondary impedance, and we get 800. That's the reflected impedance going back. Let's look at this example. This looks very busy. There's a lot of information here to learn. Given the primary voltage is 60, number of turns on the primary is 80, secondary turns is 25. There's a 20 ohm load connected to the secondary side. Determine all these. The voltage on the secondary side current, the primary current, and the reflected impedance. And we want to look at the turns ratio, the power input, and the power output. Is it a step up or step down? So if we look at this relationship here between the number of turns and the voltages, we get a secondary voltage of 18.75. And if we look at the secondary side, look at the voltage and resistance using Ohm's law, we find out we have the secondary current is 937.5 milliamps. The inverse relationship between turns, number of turns, and the current can help us to find the primary side current. And then we look at the reflective impedance, A squared times the secondary impedance, and we find out we get 204.8 ohms. The power in is the volts on the primary times the current in the primary, and we get 17.6 watts. Notice we have a lower voltage here compared to the secondary volt. We have a higher voltage than the secondary voltage here of 18, but we have, let's look at this here. The power out is the voltage times the current, and we get 17.6 watts. So we get an increased current when we have a decrease in voltage. And also look at A is greater than 1. This is a step-down transformer. Our turns ratio is greater than 1. Nameplate data. Let's look at nameplate data and try to find a lot of different types of how much current we're drawing and different things like that. So we have a transformer with this nameplate data. We have 5 kVA. We have a 240 over 120. So this could be either the primary side or secondary side, or we could reverse it. However the user wants to use it. It's a 60 hertz system. Find the transformer ratio if 120 is the secondary side. So we can do the voltages, and we find it's 2. And we know that A is greater than 1, so this is a step-down transformer. Find the current rating of the secondary. So we can use here 5K volt amps over the voltage on the secondary side, and the volts will go away, and we'll have current, we'll have 41.67. Find the current rating of the primary side. So we'll use the primary voltage here with 5,000, and we get 20.83. So we can get a lot of information from the data that's on the faceplate. Here we have electrical generator with faceplate data here, and we want to find a lot of different things. We want to look at the power triangle. So we can use, working with our units of measure, we can find how much current this is going to draw. Using the S value, 150 kVA over the voltage source that's supplied to this, we get 341 amps. And if we set up our Pythagorean's formula correctly, we'll get the correct results. If we do it wrong, we'll get the wrong results. So remember here that we have P squared plus Q squared equals S squared. And we can solve for the Q side, and we get we get this many VARs. Also, we can solve for the power factor. Cosine the angle equals, they're given the power factor of 0.85, so if we rearrange that to find the angle, here's the angle for our power triangle. Our power is calculated by the power factor times S, and we get 127.5 kilowatts for power. For homework, chapter 23, do 5, 9, 11, and 23. That's all for now. Thank you.